whether the square root of 2 or any other number belongs to Q or not may seem like a purely mathematical question with no real-world application. But I invite you to watch this YouTube video called Why It's Impossible to Tune a Piano, which explains the relationship between musical notes and not the square root of 2, but the 12th root of 2. You will be amazed to see how the two topics are related. Hello everyone and welcome to Epsilonia. This video is the first of many videos that explain real analysis. This course is called Real Analysis Part 1 and is organized as follows. It defines the real numbers and gives their first properties. Then deals with the real sequences and the concept of convergence. All of these are fundamental concepts that prepare for further advanced courses in real analysis. Like all Epsilonia courses, this will be a visual and hands-on course. Every time you see this icon, pause the video and think. We believe it's very important for you to be involved in the learning process. In this video about real numbers, I will cover basic concepts. I assume you know n, the set of natural numbers, z, the set of integers, and q, the set of rational numbers. I also assume that you have at least heard of r, the set of real numbers, or at least that you know of numbers like the square root of 2, minus the square root of 3, or even pi, which are real but irrational numbers. They belong to the set I of irrationals. In this video, I'm going to show you two proofs of the irrationality of the square root of 2. One of them is visual, fun, and I'm sure you're gonna like it. Next, we'll explore together the definition of the set of real numbers. Then we will see one of its most fundamental properties, namely the Archimedean property. And finally, I will talk about the absolute value and the intervals, two fundamental concepts in real analysis. I said I will show you two proofs of the irrationality of the square root of 2. The first one is based on arithmetic, and I won't dwell on it because it requires some background in arithmetic. I'll explain it quickly. It's a proof by contradiction, where you assume the opposite of what you would like to prove and try to get a contradiction. Let's assume that the square root of 2 is rational. Then there exist two integers a and b such that the greatest common divisor of a and b is equal to 1, and the ratio a to b is equal to the square root of 2. By squaring and multiplying by b squared, we obtain that a squared equals 2b squared, which implies that 2 divides a squared. That means 2 divides a, or a equals 2k. Hence, a squared equals 4k squared, and 2b squared equals 4k squared, or b squared equals 2k squared. This implies that 2 divides b squared, and therefore 2 divides b. Since the greatest common divisor of a and b is 1, 2 divides a and 2 divides b is a contradiction, because it would mean that a and b have a common divisor that is greater than 1. It's impossible. Something is wrong. And that something is the starting hypothesis, which is the square root of 2 is rational. That was the first proof that uses certain concepts of arithmetic. If you're not familiar with arithmetic, I will give you a visual proof without the need of prerequisite knowledge in arithmetic. This is also a proof by contradiction. We assume that the square root of 2 is rational, and we call a and b the smallest non-negative integers whose ratio is equal to the square root of 2. Here too we get a squared equals 2b squared, which has a nice geometric interpretation. A squared is the area of a square with side a, here in blue. It is equal to twice the area of a square of side b, here in red. Now we will move the two red squares inside the blue one. And we notice that there is an area that has been covered twice. Also, there are two surfaces that have not been covered. Because we know that the area of the blue square is the sum of the areas of the red squares, we can say that the area that has been covered twice is the sum of the two uncovered areas. If we do the math, we find that the little blue square has sides a minus b, and the inner square has sides 2b minus a. I recommend you hit pause and check it out for yourself. Now we will translate the equality between these surfaces by saying that 2b minus a squared is equal to a minus b squared plus a minus b squared, which is 2a minus b squared. Then we apply the square root, we divide by a minus b, and we find another rational form of the square root of 2, which is 2b minus a over a minus b. You can hit pause and convince yourself that 2b minus a is less than a and a minus b is less than b. Here we have just found two integers, smaller than a and b, whose ratio is the square root of 2. This is impossible, because a and b are the smallest by definition. Hence, there's a contradiction. This proof could have been much shorter. Assuming a over b equals the square root of 2, we show that 2b minus a over a minus b is also equal to the square root of 2, which is nonsense because 2b minus a and a minus b are smaller than a and b respectively. But without the visual interpretation, you won't understand where 2b minus a and a minus b came from. Whether the square root of 2 or any other number belongs to Q or not may seem like a purely mathematical question with no real-world application. But I invite you to watch this YouTube video called Why It's Impossible to Tune a Piano, which explains the relationship between musical notes and not the square root of 2, but the 12th root of 2. You will be amazed to see how the two topics are related. Now that we know that some numbers are not rational, we need to define the larger set to contain both rational and irrational numbers. Let's start with something intuitive. We'll take this number and we'll consider an axis that goes from left to right. By arbitrarily fixing the origin 0 and the position of the number 1, we can place all the integers, then each number x, which is written as an integer plus an infinity of decimals, will have a single location on the line. Conversely, any point y on the line can be expressed as a real number that measures the distance from y to 0 with infinite precision, and a plus or minus sign that indicates whether y is to the right or left of 0. So, intuitively, there's a perfect match between points on the line and all the numbers which can be written n plus 0 point something 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 etc., where n is an integer and each something is an integer between 0 and 9. This is why the set of all real numbers is sometimes called the real line. Mathematically speaking, this definition is far from sufficient because many questions remain open. What's the meaning of the 3 dots here? How can we manipulate real numbers? What does right and left mean? A better definition of R is that it's the smallest complete ordered field. I'll explain the meaning of each word, and I'm gonna do it from the bottom up. R is a field means that R has two operations, addition and multiplication, and that these two operations satisfy the following properties: associativity of addition and multiplication, commutativity of addition and multiplication, distributivity of multiplication over addition, existence of additive identity, existence of multiplicative identity, existence of additive inverses, and existence of multiplicative inverses. You can look at the formulas and notice that they are quite straightforward. They are the basic formulas that allow us to manipulate real numbers. That's what it means for R to be a field. Now, what does ordered mean? Intuitively, ordered means that there is a before and after, or left and right, or small and big. There is a direction. More precisely, R is totally ordered. Totally ordered means that if we take two real numbers, x and y, either x is less than or equal to y, or y is less than or equal to x. The convention is that real numbers get larger and larger as we go from left to right. Mathematically speaking, less or equal is an order relation over R. That means three things. 1. Every real number x is less than or equal to itself. This is called reflexivity. 2. The only way to have x less than or equal to y, and at the same time y less than or equal to x, is to have x equals y. This is called antisymmetry. And 3. If x is less than or equal to y, and y is less than or equal to z, then x is less than or equal to z. This is called transitivity. This order relation has properties related to the addition and multiplication operations. The first is preservation under addition. If x is less than or equal to y, we can add the same number c to x and y and the order is preserved. In other words, if x is less than or equal to y, x plus c remains less than or equal to y plus c. The second property is preservation under multiplication. If x is to the left of y, and if we scale x and y using a positive real number c, then the order is preserved. And this is true whether we scale up or down. X less than or equal to y, if and only if cx is less than or equal to cy, for c greater than or equal to 0. Defining an order relation on R allows us to define the concept of minimum. If A is a subset of R, little a is the minimum of A if and only if little a is an element of A that is smaller than all the other elements of A. This means that the minimum of a subset of R is the leftmost element, and all the other elements are on its right. A subset of R might not have a minimum, if it's infinite on the left side, for example.